Good morning, everybody. So I'll give you a very brief introduction to prophecy, hoping more and more people are familiar with prophecy and event sensing. So I'll skip the first two subjects, or run through it very quickly, and then concentrate a little more on the market requirements and where we see solutions with the event-based sensing. Concentrate a little bit more on some of the embedded vision solutions that we can bring some significant benefits, and also more machine learning and AI, of course, which is a hot subject, and the suitability of EVS, or event sensing. So you'll see EVS pop up quite often, so it means event sensors. Okay, and a few takeaway messages. So very briefly, prophecy are 130 people, based mainly in Paris, though there's an office in Grenoble in France, and then a few satellite offices around the world. We hold many of the fundamental patents on event sensing, and our products are basically sensors, so we're a semiconductor company, but we're also 50% of the company produces software also, and this is a branded software called Metavision. And of course, we provide all the development tools. So what is an event sensor? So let's compare it to CMOS sensors, we all know. So frame-based sensors are clock-driven, produce fixed amounts of data, and need an exposure period to produce a meaningful image. Event sensors are very different, so that we actually generate an event as it occurs. So it's asynchronous, it's not part of a frame, it's scene driven, so the latency can be down to microseconds, which in frames per second equivalent is tens of thousands, for example, of frames per second. And it becomes very efficient data to manage for computer vision and machine vision. Of course, it doesn't produce nice images, so in consumer type applications, it can work with conventional sensors, for example, to bring many benefits. So let's compare. This is an event image, a stream. Okay, so you can see on the right there's a graph showing the data rate, so data bandwidth, which is scene dependent. Obviously, when the car is moving, then there's more data generated, and when it stops, then only the movement in the image is seen. The reason you see blue and black is because we code on events and off events, meaning positive changes and negative changes. Okay, so we work on this contrast change basis, okay? And as a result, we consume far less bandwidth compared with a regular frame sensor, which you can see in orange here. The other thing that is, I think, pretty powerful is that event sensors do not exhibit any kind of motion blur. There's no exposure mechanism, so anything that's moving during the exposure time will not create a blur. All it will do is create an event, which is a discrete point in time. So no pixel exposure and frame concept down to tens of microseconds of latency makes these very good for high speed imaging in machine vision particularly. And you can see there's an image here of an ambulance, for example, taken with a conventional sensor, and the one to the right is being corrected with event data. This is why we can actually read what's written on the ambulance. They're inherently HDR. So as you can see on the image, basically as we're coming out of the tunnel, you can see all the detail in the image, whereas the conventional camera will obviously have lots of issues with blooming, and we're capable of getting up to 140 dB of dynamic range with event sensors. They also work very well at low light because it's working in a differential way and not absolute. Then we kind of have a kind of noise filter. Okay, so let's talk about some of the applications. So first, what does everybody need? So increased productivity. I think this should really mean throughput. So getting things through the production line faster and faster. Also, the market is very crowded, where people are using the same sensors, and that becomes an issue where, you know, basically you start to play on pricing and other things instead of having some technical differentiators. So event sensors bring something new to the table. Okay, we can reduce system level costs again through lighting and power, and they're ideal, as I'll show you later, for any kind of edge processing. So machine learning, AI, they're very well designed for that. Okay. So some of the applications we have are actually things like high-speed counting, measuring. They work well in 3D, so you can have very fast 3D measurements in the range of hundreds of frames per second equivalent, or hundreds of point clouds per second, I should say. Great for defect detection and AMR guidance, anywhere where you need to take decisions very rapidly. Okay, and also you can see some other applications taking advantage of the high dynamic range, so things like welding. We can do logistics and direct part marking, barcode reading, again at very high speed, and being able to accumulate edge data as well to increase the spatial resolution, basically, by using this high temporal resolution. So also in fluid dynamics, spray plume monitoring. Again, many of these applications are visible on our stand, so we'd be happy if you swing by and have a look at some of our demos. Okay, so customer perceived value. Obviously, the ability to reduce system illumination and costs is a major benefit. The fact that we don't have this blurring issue to deal with means that you can actually, you don't have to compensate for short integration periods with high lighting levels. So we can effectively reduce the lighting. The ability to do depth measurements, extremely fast sorting and barcode reading, as I say, and OCR. And then even things like motion detection and context awareness, and this really can be used in different tracking, tracing, and triggering even of a high performance frame-based sensor by using the advantages of the event sensor. Okay. So another application we can show on our stand is using a concept of active markers. So an event sensor can actually do filtering in the time domain. So in other words, we can do low pass, high pass filtering, notch or band pass filtering on temporal data. So in other words, we can recognize frequencies, reject them, or focus only on those and reject everything else. And this is what this application is doing. So it creates 100% background removal, And what we can see is only these ID markers. And if we modulate the pattern, then we have a unique ID for each of the marker. So applications, real-world applications for this are 3D pose estimation. So this could be used in crate, loading containers, production lines, anything you like. Factory construction, site safety systems, so safety zones, for example. This is a good technique for having ultra-fast and reliable safety systems. Localization and ID for AMR, for example, and drones. And again, on S29, just along the way, you can come and see this work. Okay, so for embedded vision, this is obviously a new direction that we are developing more and more reference designs, or what we call starter kits. One of such is with the AMD Crea. So this is the K29 SOM, but it's designed to use with the AMD Crea KV260 Discovery Kit. So this is compatible with our IMX636 sensors, which we developed with Sony, and our more recent Gen X320 sensor. And this is provided with an application, so basically out of the box you can start getting something working. But the whole idea of this platform is to allow customers to develop and move to deployment easily. So we provide the reference design, which is the hardware and the interconnect, and the software. Okay, so this is Vivado Pentalix version, and all the software and drivers for an example application. In this case, it's the active markers demonstrator that I mentioned in the previous slide. Okay, so we are actually, that's just one of our kits. We have others for MCU platforms, for the STM32, for example, based on our Gen X320, and we are developing more and more going forward, which we will announce shortly. Okay, so I mentioned that event sensors are ideal for machine learning applications. So why do I say that? So ultra low latency, obviously that's having the high temporal resolution means that you can take decisions much quicker. And inference at any rate is possible, only limited by the compute platform. Okay, we are able to generalize easier. What does that mean? Basically, the light variation means that we can have a single data set that performs the same in nighttime or daytime. So data sets are obviously expensive and laborious to manage. So the ability to you simplify the models is really quite powerful. Data sparsity, of course, then right from end to end, basically means you can develop more elaborate algorithms and perform with less power. So our MetaVision software, this is something that we are now offering for free with our evaluation kits, but can be purchased should somebody buy a third-party camera with the event sensors. They can actually purchase our MetaVision SDK. Okay, and the SDK basically has a number of lots of different calibration and other features, but also a very interesting machine learning part as well. So where you can do detection, optical flow, gestures, classification, and then for data set creation, event to video or video to event. Okay, so let's look quickly at a few detection and tracking using machine learning algorithms from our MetaVision software. Okay, so this is a a vehicle tracking and classification. Okay, and a similar one for people detection and also mapping their trajectories and speed. Okay, so I mentioned our MetaVision software. So it's a very comprehensive software with machine learning toolkits, but also 95 ready off-the-shelf tested algorithms, code samples, and tutorials. Okay, so it comes with 6 basic modules. We also have an open EB, so for the Linux community, then we have the open source architecture available as well. Okay, so just some of these things running in real time. Okay, so that's basically all I wanted to show you for today. So a few takeaways. As I say, event sensors are ideal for machine vision and motion understanding capabilities. They do this by design. They're a great match to machine learning, particularly spiking neural networks, because they work in the same, under the same principles, and that would offer the lowest latency and lowest power consumption for more and more complex tasks. So we're seeing more and more platforms, for example, by various SoC manufacturers implementing SNN techniques, although they work very well with conventional neural networks as well. And this year, in fact, at the Vision show, we are showing 3 more machine vision camera makers from some of the major names in the business that have implemented our event sensors. Okay, so, and of course we'd be happy to see you at our stand in this hall, S29, and show you around some of these demos. So thank you very much.
Well, allow me one question. So this is a very interesting technology what you described here. What do you think? What are the next logical steps in the exploitation of this technology? Is it okay to speculate a little bit?
We see a lot of traction in some of the more emerging markets. So again, where AI is required, but particularly in things like AR, VR, particularly AR. So where it's solving some major issues with power consumption, for example. And again, although it's not necessarily consumer AR, of course, this can be professional applications. And one of the major issues they have is trying to wear smart glasses for a whole day when they heat up on both sides. So this is really quite a significant issue to fix, and this is where we score very high points.
Okay, I'm curious to see this. Okay, so thank you very much.